Rolf, maybe you should maybe you should start
Sure. No problem. Yeah. So hi guys. Hi everybody. I'm Rolf Brink, CEO of Asperitas, and also leading the immersion workstream within ACS. And within that, we're driving the immersion developments across the industry and working closely together also with the other project leads as well as the ACF project lead. One thing I just want to mention is that. Hi guys. Hi everybody. Somebody is off mute while listening. And also lead. Yeah, thanks, Don. Don, you might want to disable the audio on the web page and just use the audio of the Zoom's meeting. That will prevent some issues that you had earlier on as well. Just giving you the heads up. So I would also like to extend to the community that is listening into this session. We would love to have you join the conversation if you have. If you're ready to engage with Dale and the rest of the ACS leads here, please use the Join Now button right underneath the live feed and start up your Zoom session. And you're welcome in this conversation to join in.
Don, you want to say hello?
I'll give it a shot. Can you hear me now?
Yes, perfectly.
Okay, so I'm Don Mitchell, and I'm really not ACS. I'm ACF, as in Advanced Cooling Facilities. And this project started up beginning of August, looking at harmonizing the integration of the Advanced Cooling Solutions team solutions into data center facilities. And I love the lead in from Dale. There's a lot of refined solutions for deploying liquids in data centers. Typically, those work very well when they're done at day one. What we're trying to do is define the practices to make it so you can add liquids at year 3, which seems to be a growing need in the industry, especially as the industry moves towards slab floor. A lot of the myths and religions around liquids need to be reevaluated and determined, are they necessary? Well, when they're done at day 1.
Well, okay, Don, we made an exception to let you in. Welcome. And we'll move to Michael now.
Yeah, Michael Berchtold with Intel, and I'm leading the ACS cold plate track. So.
Jacob?
Yep, my name is Jacob. So I'm leading the door heat exchangers along with the John here. I would like to have a John also talk a little bit about himself. So we are coming from the Facebook, driving the door heat exchanger in the ACS group. Hey, John.
Yeah. Let me turn my video on. Yeah, so thanks for that, Jacob. Hey, everyone, my name is John Fernandez. As Jacob just highlighted, we are thermal engineers from Facebook, and we've been supporting the ACS door heat exchanger sub-project.
So, Rolf, did I leave somebody out? Great. Okay. Michael, I think we're ready for the first question.
I want to make a comment before we start.
What a shock.
Thanks for that, Jacob. Hey, everyone, my name is John Fernandez. As Jacob just highlighted, we are
Yeah, I'd like to remind everybody who's in the Zoom call to kill the web session, because the audio will be interfering with the Zoom meeting. The Zoom meeting is about 1 minute ahead of the web session, so you all just time traveled.
Can I make a comment?
Yes, but Soma, can you mute your effing virtual page first? We're hearing a loop.
Ah, quiet. Go ahead, Shlomo. Well, now you're on mute, buddy.
Okay, I'm unmuted. Okay. So you made a comment in the previous presentation, which was very important. And when you said something, what I'm trying, should I talk or not? Can I?
Soma,
Some of there's two different audios right now. You joined the Zoom call.
Okay.
And that's how we're talking. If you wouldn't mind muting the FinTech webpage, or even just exiting out of it for right now, that's what's causing that feedback loop. And whenever you're talking, we can't understand what you're saying. So now go ahead and give it a try.
I think.
Can I? Am I okay now?
There's two different audios right now.
Yeah, I know.
Join the Zoom call. Okay. And that's how we're talking.
Shlomo, just get out and come back in all together,
Okay.
That won't fix it.
and then just join.
I've just put him on mute, guys. So,
the F and virtual.
so Dill, do you want to start engaging with your plan?
Sure. Well, I think that Michael had some questions already in the queue, so I think we should go ahead and proceed with what our broader audience wants to talk about or has to say.
How do I get out?
Huh?
So, Dill, do you want to start engaging with?
Okay.
All right. Michael, you're on mute. I think you were talking.
Yeah, sorry about that. I think I may have to engage with Slomo offline to try and get that fixed. Yeah, there were a couple of questions that were in the chat. Sorry, in the comment section of FN Virtual. If you guys want to scroll through there. Other than that, I think we covered most of them. And then let's see. Amir Reza, I think you had a question.
Dill, I suggest you get going with your preparations. Okay.
Sure. I was just quickly scanning the questions that Mike mentioned in the chat, but I agree. I think we should move on. So those on the panel, as well as others that would like to chime in, do you see the different cooling systems in a single water loop as an issue or an opportunity?
This is Reggie Gnaffer. I look at it as an opportunity. We're actually working with some companies right now trying to implement cold plate technologies for GPUs. So I think it's an exciting opportunity. And water has been around for decades, right? IBM thermal conduction module, and a lot of the problems that people still think about has been solved, quick connects and so on and so forth. It's just, there's just a bad feeling about water. So I think it's exciting. And it's also exciting to see a guy like John Fernandez leading this thing. So I think things going to look good. Right, John? Thanks.
So what do you see as the opportunity there, if you don't mind me asking? Is there a specific opportunity that you're seeing?
Was liquid cooling?
With the different temperatures, with the different thermal requirements?
Say it again. Say the question again.
The question that Dale asked is these different temperature requirements, the different thermal properties.
Yes, I think that you can control the flow to go where you want it, even if you don't have a dynamic cold plate. Even if you use the current technology, I think it's possible. First of all, was thermal shadowing is not that much of an issue, right? Was liquid cooling, right? We've looked at it. It's compared to air is significantly smaller. And I don't know if you're talking about indirect liquid cooling or direct liquid cooling. If you talk about direct liquid cooling, obviously is a lot easier because you don't care about where the fluid goes, right? But you're going to get a little hit on thermal performance. But I think the indirect liquid cooling cold plate was improved technology in terms of mini channels and so on and so forth. I don't want to say micro, but more mini channels. I think it's going to take us a long ways. And Yeah.
All right. Was there others that have a comment on basically multiple cooling systems on a single
Yeah, I
water
did.
loop?
Am I okay now?
Much
Am I
better,
okay now?
Shlomo. Go ahead.
Okay. So you made an important you made an important comment in the previous presentation.
All right. Was there others that have a comment on basically multiple cooling systems on a single water
Can
loop?
you please close the web browser?
Much better, Shlomo.
Okay, so if basically one of the things what you said in the previous presentation.
So Shlomo,
Sorry, guys. Let's continue.
I'm gonna have to mute you right now. We're getting a feedback loop. I did email you with some instructions on how you can close that web page. So if you could read those instructions and maybe try and rejoin, then we won't have this feedback loop.
Is there others that would like to comment on this idea of multiple systems on the same water loop?
I'll give a shout out to Tim Chambers. Say something there, Tim.
Yeah, I've been waiting for him as well to come in.
Yeah, I think we did find it an opportunity. We did do the cascading, and it was a great way of mixing technologies together. And it allowed you to actually mix and match different solutions across the same data hall in the same water loop. And it was a great way of effectively bringing efficiencies. So if you think about it, you're really working off the end of the loop, in our case, which is immersion. So yeah, we saw it as a big opportunity and proved the fact that it did actually work, which was quite satisfying.
So can you describe the type of thermal environments that you've hooked up together in that sense?
Right. So we started off, I suppose, in what we would call our traditional build was like an octile environment using in-row coolers. So they started at our lower sort of temperatures. So go back to the chart you had with the temperatures. We originally designed that to feed around 24 degrees. What we then did, we moved on to an LCP type solution, which is the Rittel in-row type solution, where we could take the temperature up slightly higher than those. So the waste heat from the original in-rows became the, if you like, the start heat for the next set of in-rows. What we then found was the next, if you like, level of technology we could use quite comfortably was to put rear door solutions in there. So we then went into a U-Systems rear door, where again, we took the temperatures up, and then we used a mix of on chip at that point to then take a starting temperature into the immersion unit, which was Rolf's asparagus units. So we effectively lifted the temperature up through the data hall. We were very, I suppose, lucky in the fact that we could actually deploy the kit in the order we wanted to, and it certainly creates more interesting fun when you try and mix and match solutions later on going forward. But we built it in an environment to prove the cascading did work. We've been working on, I suppose, different ways of doing this where we would blend loops together, or else on a larger site, build it in separate chunks. So you'd actually have the different types of technologies in the sections, which would then link back into the water system. But as far as our test solution we built, we were able to actually have the kit in the right place at the right time, if that made sense.
All right. Well, I think that was a softball question. And I think I'd like to go to a more controversial question where there might not even be an answer. And that's there's a growing controversy in terms of, the density is getting higher and higher. And there's some vendors that tell us that they're going to have to go to very cold water temperatures in order to cool that high density, so that we're no longer going to be able to use warm water cooling. We're going to have colder temperatures. So in theory, there's a trade-off between, say, energy efficiency and a simple compressorless system versus, say, performance of the IT equipment. So which side do you optimize? Where are the trade-offs between those two?
Do you want me to go?
Is there a way of looking at this and comparing that to the car industry? Actually, it's a bit rhetorical coming from me in that sense. So let me just give an example. In Formula One, nobody cares about how much fuel is being consumed as long as you win the race. right? That's the only thing that matters. Just squeeze that little bit of speed out of it. Whereas we will never see those kind of Formula One cars on the normal road. Right? So there's a difference between this level of high performance where you always need to squeeze out the last bits and bytes at the highest, just tiny little bits of clock speed, as opposed to mainstream data center use, mainstream platforms, enterprise deployments, normal applications that are rolled out at massive scales are very often not these type of HPC platforms. So I'm not sure whether it's an either or. It's an overall efficiency question, if you ask me. That if you have that specific requirement, of course you're going to utilize liquid cooling because it can deliver you more power in terms of compute. Whereas all the other types of platform will utilize the benefits of liquid cooling because they don't need the chillers anymore. So there's always going to be that division. I don't think, honestly, that there is going to be that this question is valid as an either or question. Does that make sense?
True. That's true. I've seen some supercomputer centers that have, they use whatever water is available. So when it's cold outside, they can cool with a lot cooler water than their design temperature, and they can run their processors what is called turbocharge or turbo mode. So they take advantage of the cooler water being available to increase their scientific output. Other comments?
We make the topic too complex sometimes, and we use the term cooling versus just heat transfer. The reality is we're not trying to cool anything. We're just trying to take the heat from one point and take it to another point. So as you get to higher densities, you need to have a higher density or higher capacity way of transporting heat. Liquid does that. Anyway, let's just keep it simple. Just talk about heat transfer is the issue, not what the absolute temperature is.
I have a comment here. Are we talking about higher, flux distribution? Because you're going to have non-uniform flux distribution. Because of that, you're going to have very high junction temperature, which means typically you got to cool for the highest junction temperature. That is a different problem, right? Should we talk about that? In other words, when we say about high heat flux, you're going to have 3,000 watts per centimeter squared on a very, very, isolated point where the rest of them might be 80 watts per centimeter squared. So, because of, core stuff and all of that, should we be talking about non-uniformity and power and corresponding flux and temperature distribution? Is that an issue we need to talk about?
It was an issue that was addressed earlier on one of the seminars at the beginning of the day, where they actually looked at the just the design of what you're trying to do with liquid and immersion cooling. I don't know if it'd be neat if we had some of those slides present right now, but this topic was addressed to, I'm trying to think which session it was. You recalled there, Dale, or did you get a chance to? I'll dig it up.
I think another thing to note is that it also depends on how hardware evolves over time, right? And how the components evolve over time and how they drive these cooling requirements. So as someone on the hardware side, you don't necessarily want to go to your data center guys every 5 years and say, hey, can you drop the facility water temperature by 5 degrees? Because it takes very long to design and sort of install these units. So I think there's some middle ground that's necessary there. I think another aspect to take into account is also silicon processing isn't growing as quickly as it used to before, right? I think we are starting to, a lot of people talk about the limits of Moore's law, right? Or reaching the end of Moore's law. So this is a really interesting time because you obviously want to run your entire facility very efficiently using the least amount of power and the least amount of water and so on and so forth. But there's a middle point because performance is important too, because that's what generates revenue. So there's a middle ground that needs to be established over there. And hopefully these sort of discussions sort of allow us to focus on that and determine, like for one point I think that's been going around with harmonization is like, what should the supply temperature be? So that might be one aspect. So anyway, just another.
Yeah, I think those are really good points. And I think the other point I want to make is back to the idea that users can help drive this. I mean, if we as buyers and consumers say we want to keep the warmer temperature cooling, innovative technology will figure it out. I mean, when we were first establishing the W classifications, multiple vendors told us flat out that they could not do it. And fortunately, there was one major vendor that said, yes, we can do it. And, we issued those, and now there's a lot of vendors that can do it. And in fact, other labs like NREL put out a bid before there were products available. And they got bidders to be able to provide what they wanted. So, I look forward to innovation being able to continue the ability to have our cake and eat it too, to be able to have high productivity of our compute, as well as to do it with compressorless and hopefully even waterless systems.
There's kind of an extension to the analogy that Rolf drew a while ago about Formula One. Yes, we're talking about Formula One data centers, and these are not the mainstream data centers that will make up most of the revenue of the companies that build all this equipment. But what's true in Formula One is that, just like going to space, there's a certain amount of technology that flows down to the rest of industry and the rest of the general public. And I think what the opportunity is, going back to your actual question, Dale, what's the opportunity, is we have to learn some things about how to make best use of the water temperature that you can actually get by going straight to the outside. I don't know that you need to get it any colder. We just need to use the water better and make better heat transfer choices, and then teach the rest of the industry how to do that. Because I think among everybody that's on this screen right now, I bet we all know, like we're pretty close, right? I think we all could get together in a room and come up with something that worked for almost everyone. But it has to be able to flow down to people who will actually pay for it all. For the sake of people who are making some of this equipment, right now for us, there just aren't enough people who are buying it. And it won't really move until people are really buying it.
Part of the challenge is reliable performance rarely gets much attention, or near as much attention as unreliable performance. So you can have solutions that work a whole bunch and have no problems for decades, but someone makes one wrong and it creates a whole religion around, we can never have that happen again. And it never needed to happen the first time. And I think that's one of the challenges. One of the things I love about Dale's discussion is he's not presenting something new. He's got solutions that have been tested for decades. But over the decades, people have made mistakes. And people remember the mistakes. They don't remember the fact that for 30 years, an HPC data center was working fine and had no problems. That's probably the biggest challenge we face right now, is the highlights of failure exceed the rather boring existence of reliability.
So Don,
but the times are changing, right? To be honest, I mean, especially on that same note, Don, I think that's a great point you're making. Exactly, and I think every engineer, and I think we're in a community of engineers right now, especially during the Tech Week. I think one of the things that I've learned a long time ago, you learn from your mistakes. That's why you know so much, right?
So I think in our last couple of minutes, we ought to give Shlomo one more chance at solving this audio problem. So go ahead, Shlomo.
Does it work now?
And I think every engineer, and I think
you still have the audio switched on your web browser,
I switch it
which
on
means
now.
that you're having dual audio feed.
Soma, could you mute the volume coming from your computer? We'd be able to hear you then. I sent you an email about this.
Shlomo, if you'd like to type your what you want to say in the
How
discussion.
about now?
on your web browser.
I switch it
which
or
means
not?
that,
No.
that you're having dual audio. You have to turn off the F&Tech application. There's a reason they call it F&Tech, okay?
I think we're not supposed to say that out loud.
Shlomo, do you think you'd be able to type it into the chat box? I know these guys definitely want to answer your question.
Yeah, as he's doing that, Dale, can I make a point?
Absolutely.
Yeah, so I'm concerned a little bit about the divergence of packaging, with ITRS now stopped and it's really heterogeneous integration. So we start stacking things up 2.5D, 3D. Are we aware of where that technology is going? Because certainly you're not going to be doing direct liquid cooling because you have, chip to chip issues. Is that something that this particular group need to address? What about packaging driving performance? Sort of like what John said. I mean, to a certain extent, packaging is going to drive performance because the frequency between nodes is what, 4, 5, 6 years now? So is that something that you guys going to address?
Michael, this one seems to be right up your alley, right?
We're definitely seeing more stacked, but I mean, the overall thermals are kind of kept in consideration. Can we cool it with liquid cooling? Internal package die-to-die conductive hats are considered. And if one company doesn't do it well and another one does, then there's competition out there still. So I don't know if OCP is necessarily driving anything in particular for it. But definitely the better, liquid cooling infrastructure that we can have out there, the more of these technologies we can experiment with and work with.
Favors and all, right?
Yep.
Yeah.
Well, all right. Thank everybody for your time. I think it was a lively discussion, and we look forward to continuing it over the course of the next couple of days.
Thanks very much for your time.
Right.
Can I try to talk now?
Oh, you finally
Working.
found it.
It sounds like it's working.
Oh, come on. Let's
Perfect.
go.
Yeah, we can't stop now.
So the issue that I have is that we are focusing on coming up with requirements and specifications for liquid cooling so we can make make it easy. But we are doing it without looking at the main motivation that we're trying to do. And basically, if we want liquid cooling to be successful, I think the number one thought before we do anything is liquid cooling needs to be commoditized. What I mean by commoditized, liquid cooling needs to be like air cooling used to be. Air cooling is commoditized today. Vapor chambers, vapor chambers, heat pipes used to be, if you remember, $50, $20, $30 a pop. But they're all commoditized and everybody is using them in air cooling and it's very easy. Liquid cooling today is very complicated because everybody is trying to come up with a way of making it work. The way to look at it is if we start with a thought, everything we do, let's assume we look how we do a liquid cooling system with cold plates. The number one thought is how do we make sure that we can commoditize the system? To commoditize the system has to be foolproof while at the same time reliable and while at the same time low cost. If we use a criteria like that before we decide what our spec looks like, what do we need to do, then while doing it, we would identify the liquid cooling, call it technology or process or whatever it is, that would at the end make it for us or for the market, would enable developing the technology. That does not happen today. Intel started with all sorts of processes of coming up with spec for material, for fluids, and it's not necessarily the right fluids because Intel came up with water with additives. Most people which are doing liquid cooling today do not use additives. They don't use a glycol, I'm sorry, but they're using anti-corrosion, antibacterial, but you don't necessarily need to use glycol. So what I'm saying is if we really figure out the goal in that fashion, that at the end of the day, it has to be commoditized, we would come up with the right answer. That's my opinion.
Well, I think we're going to have to end on that note, right, Michael?
Yep,
Yeah, we-
commoditize is good.
We actually have a break next session, so if you guys want to talk for a couple more minutes, you definitely
Right.
can. But we do have
I would like to hear feedback, if anybody, if it's possible.
Yeah.
So
Well, I think this is exactly what OCP is all about. What these work streams, what advanced cooling facilities, what advanced cooling solutions, immersion work stream, cold plate and rear door cooling. That is exactly what we are trying to achieve. We're trying to harmonize technologies to make sure that this can become a commodity. And to be honest, what I'm seeing and feeling on a daily basis around me in the industry, with customer engagements, with the industry engagements, is that we're right now. You guys are all familiar with the famous startup picture, right? With the chasm, the crossing the chasm bit. I think we all have crossed the chasm. To be completely honest, the technologies have now crossed the chasm. Everywhere you see activity brewing around liquid cooling, and that's rear door coolers, cold plate, and immersion alike. Right? There's not a single hyperscaler that hasn't started deploying liquid technology. Immersion is being deployed, and what we're looking at here with the harmonization efforts, and also with the current projects, we're looking at new server developments, helping out OEMs to start generating designs. It's going to take a couple of years, mind you, because these kind of things take time, sometimes even up to 10 years, 20 years, 30 years even. But right now, the industry is now all looking at liquid cooling. There is nobody else caring about air cooling at this point in time anymore, if you ask me.
Yeah, so everybody is looking at liquid cooling from the wrong way. So let me just make a small observation. And I know Michael knows about it. And I've been talking to Intel about it and to other people. If you just make a simple comment, a simple twist, instead of doing positive pressure liquid cooling that everybody is doing, if you move to negative pressure water cooling, if you start thinking through it, if you look at the experience that we have at Sandia National Labs with negative pressure, if you read the white papers that Sandia has written about their experience with negative pressure water cooling, that will show you that this is a path. Negative pressure water cooling could solve the issues with connectors, which are extremely expensive. You don't need those. They solve the issues of reliability because it never leaks water. And when you do an upgrade of your data center and system, you don't need to shut down everything. You can do everything while the system is running. This is only if you have a complete negative pressure water loop.
Well, I think that many vendors will argue that their system is also bulletproof, cost-effective, et cetera. So I don't think we're going to have an agreement on one technology dominating the rest here today, Shlomo. But I think that the goals that you outlined were certainly ones that we all agreed to.
Well,
so Dale, certainly negative pressure removes some of the risk.
Yes, that's
you don't have to adopt it. It doesn't have to be a standard, but I wouldn't have been able to deploy a liquid cooled system, nearly 10 years ago if it had been positive pressure.
Well, if you look at the whole data center, and you're in a data center with positive pressure, you will have millions of connectors. Those little connectors that the pair costs today $20. Those connectors, despite the fact that they could be aerospace quality connectors, but we're talking statistics. If you have 1 million connectors, some of them would leak. And a leak in a rack, which is $1 million rack, could cause $1 million damage. This is with a $20, if you want to call it, connector. So what I'm saying is, if we are looking at items that we could eliminate and remove from the things that cause problems, one of them is the connectors that I meant, because all the connectors today, whether it's on a rear door or whether it's on a cold plate, they have to be first class quality and even then, with positive pressure, you will get leaks. You cannot avoid it. If you go negative pressure, you could avoid it. So I'm not saying which company, who does what. I mean, negative pressure could be developed by multiple companies. There's no rocket science here.
I heard that negative pressure sucks.
That's okay.
Absolutely.
Listen, I'm
Yeah,
okay.
you don't get leaks. Plus with negative pressure, it's easy to detect leaks because you can just monitor your vacuum pump activity.
Correct.
Shlomo, that was a pun that Don said, just in case.
I know.
Okay.
Yeah.
I will say I did visit a negative pressure facility. The brand new Nautilus facility is a negative pressure. But I also think that, and I don't know if Patrick wants to speak or not, but you've operated a data center, I think, at positive pressure for a while, haven't you there, Patrick?
Yeah, for about 20 years, actually, OVH has been doing somewhat positive, not that much positive, actually, very, very low pressure liquid cooling. And we've done that for, about 500,000 servers, so over the time, I think it's a couple million servers that actually went to water cooling. Yes, there's been some leaks. Yes, that happens. But with the right attention, the right technicians, people who know how to operate them, you can really limit the issues that you find there.
So I used to be a positive pressure bigot. I'll admit, I converted a few years ago. It just when you understand the limitations that we're mentioning and the issues with positive pressure, and you compare it and you look at the negative pressure, that really gives you the indication on how do you resolve those issues, which are still associated with positive pressure. Now it may take some time, but don't forget, if you look at the market today of liquid cooling, it's nothing. It's so tiny. So the opportunity now, because the market for liquid cooling is going to explode within a couple of years. So now's the opportunity to figure out what's the right technology and implement it. And that's the way I look at it. And as I said, my experience now is the only way to avoid many of those issues is by having a secondary look at negative pressure.
All right, Dale.
So Dale, did you talk about my soapbox? I always worry about making sure the connections, your supply and return, are dissimilar. Because
I was thinking about you, Steve, because there was a presentation on the connections and the connection standards, and they talked about not only color coding but physically not being able to do it. I go,
absolutely,
Steve is going to love this.
Absolutely. You don't. I've had two facilities where people have cross-connected, and it's a disaster. They should not. You should not be able to connect your supply to your return. Not ever. Just remove that.
Not ever. You're right.
Yeah.
So I'm glad folks are thinking about that in the standards, not just.
There's a white. As I understand it, Rolf, correct me if I'm wrong, but there's a white paper coming out, or maybe it was Michael. I can't remember now which.
Yeah, there is a universal quick document coming out. Yeah, tons of white papers. Yeah.
But yeah, this also goes into the domain of ACF where Don is, right? This is one of the outcomes that we had last year during the Tech Week, that we because this is pretty much something that is very easy for technology vendors to design against. What companies like Asperitas, for example, just are waiting for is a set of common requirements that we can that ACF comes up with. Okay, from now on, these are the specifications that technologists need to comply with. Then I can go to my design team and tell them, okay, now we're going to check. From now on, our interfaces are going to change into this, right? That is exactly what we're waiting for, so that we can make sure that we can interface with the same interface that everybody else interfaces with, because that should solve a lot of the harmonization problems. Right, Don, you are on mute. I saw you were trying to speak.
Yeah,
up,
I tried to mute because I didn't want to interrupt your wonderful introduction to what we'll be talking about. I will say that the discussion on negative pressure is an interesting one, and it does tie into what we're trying to do. The ACF, Advanced Cooling Facilities, is a fairly new group. We have not looked at specifying the negative side. I will tell you that there are situations, in some cases, that negative pressure can make some situations, it makes the impact of a leak less, but in some cases it can have greater problems in terms of it's just a different design on your gasketing and other things. And if you're not designed for negative pressure, you'll have connections that will have a greater probability to leak in negative than they would in positive, except for you just won't have an impact.
They never leak. With negative, you never leak, because when anything leaks, you're getting air leaking in. You never get water leak out. That's the key. And
you get a situation that needs to be repaired. Okay. And so that ends up being, if you have connections that need greater repair, even though you're not cleaning up after them, you still have to figure out how you're going to do your concurrent maintainability.
I will get you down to. I'll get you down.
Concept is negative on the.
No. I'll get you down to Sandia. I mean, I'm not joking. Go down to Sandia, and I'm not saying, and take a look how they do it. And I'm not saying.
I'm not saying that it's not good. I'm saying that every solution out there, there's a lot of great solutions that work great without being negative pressure. And it's just that so the challenge, just like the AC versus DC discussion, it went on forever, which is better. And I'm not going to go through, and we're already pinging on the next session. So, but I do want to take this offline. It is something that ACF probably should look at. And we're not prepared to be talking about it this Thursday, but we will take it under advisement for future.
But
sense.
Don, it's on the other side of the CDU. I don't see your group taking it on, because it's on the server side of the CDU.
Well, I will tell you that I have seen situations where and maybe that's where I'm maybe seeing the opposite on the tech side. Yes, but I'd also say that if you look at Nautilus, they did a whole data center using negative pressure rear door heat exchangers.
Hey guys, this has been a fantastic discussion. I really hope we keep it going either on project calls or online here. But we do need to move on to the next panel.